You are sitting still right now, or at least that is what it feels like. The coffee in your cup is not sloshing. The pictures on your walls hang straight. Every sense tells you that you are at rest. You are not at rest. You have never been at rest, not once, not for an instant in your entire life. Right now, Earth's rotation carries you at roughly 1,674 kilometers per hour, about 1,040 miles per hour near the equator. Earth orbits the Sun at 29.8 kilometers per second, roughly 107,280 kilometers per hour. Our solar system orbits the Milky Way at 220 to 230 kilometers per second. And relative to the cosmic microwave background, we move at 369 kilometers per second, traversing 31.9 million kilometers every day, a distance 83 times greater than the gap between Earth and the Moon. All of this happens while you sit perfectly still. There is no such thing as absolute rest. The concept does not exist in physics. Motion must always be measured relative to something, and different reference frames give different answers that are all equally valid. By the end of this video, you will understand how Galileo glimpsed this nearly 400 years ago, how Einstein transformed it into modern physics, and how massive rotating objects like Earth drag space-time around with them, an effect so small it shifts satellite orbits by less than 2 meters per year, yet so real we have measured it with orbiting gyroscopes. If you find these explorations valuable, consider subscribing to the channel. Now, let us begin. Let me start with a thought experiment that changed physics forever. One proposed by Galileo Galilei in 1632. Imagine you are below deck on a large ship, enclosed in a cabin with no windows. The ship is moving in a straight line at constant speed across calm water. Inside your cabin, you have butterflies flying around, fish swimming in a bowl, water dripping from a bottle into a container below. Galileo asked, "Can you tell from any of these observations whether the ship is moving or standing still?" The butterflies fly equally in all directions. They do not cluster toward the back of the cabin as if blown by the ship's motion. The fish swim just as easily toward the bow as toward the stern. The water drops fall straight down into the container, not at an angle, not lagging behind as the ship moves forward. No mechanical experiment you perform in that cabin will reveal whether you are moving at 10 knots, 20 knots, or sitting at anchor. The physics inside the cabin is identical regardless of the ship's uniform motion. This is Galileo's principle of relativity, and it overturns a natural assumption. We tend to think that motion is something absolute, that an object is either moving or not moving, full stop. Galileo showed that uniform, straight-line motion is undetectable from within. There is no experiment, no measurement, no observation that can distinguish uniform motion from rest when you are inside a closed system. This might seem like a philosophical curiosity, but it has profound implications. If you cannot detect uniform motion from inside a closed system, Then what does it mean to say you are moving in the first place? Moving relative to what? The shore? The ocean floor? The center of Earth? The sun? Each of these gives a different answer, and Galileo's thought experiment suggests that none of them is privileged. There is no experiment inside your ship that will tell you which answer is correct. The concept of absolute rest begins to dissolve. I remember when I first truly understood this, and it took longer than I expected. The intuition that motion is something you either have or do not have runs deep. We speak of cars moving, of people standing still, as if these are properties of the objects themselves. Galileo showed they are not. Motion is a relationship between objects, not a property of any single object. Think about what this means for your everyday experience. You are sitting in a room which is attached to a building which is attached to Earth's surface. Relative to all of these, you are at rest. Yet Earth is rotating, carrying you eastward at over 1,000 miles per hour if you are near the equator. Relative to Earth's axis of rotation, you are moving constantly. Earth is orbiting the Sun, so relative to the Sun, you are moving at about 66,661 miles per hour. The Sun is orbiting the galactic center, so relative to the Milky Way, you are moving at roughly 500,000 miles per hour or more. Each frame of reference gives a different answer, and according to the principle of relativity, each answer is equally valid for describing the physics. There is no master frame, no absolute background against which your true motion can be measured. The question, how fast am I really moving, does not have a single correct answer. It only has answers relative to chosen reference points. This was Galileo's insight in 1632, though he could not have known how far it would eventually reach. Let me go deeper into Galileo's thought experiment, because the details reveal just how carefully he reasoned about motion. Galileo asked you to imagine being in the cabin of a large ship, shut away from any view of the outside. In this cabin, you have various things to observe. Butterflies fluttering around, fish swimming in a bowl, water dripping from a bottle into a container below, incense smoke rising into the air. If the ship is anchored in harbour, perfectly still, you observe all of these things behaving normally. The butterflies fly in all directions with no preference. The fish swim toward any side of the bowl equally easily. The water drops fall straight down. The smoke rises straight up. Now suppose the ship begins moving at constant speed in a straight line across calm water. No rocking, no acceleration, just steady motion. What changes inside the cabin? Galileo's answer was, nothing changes at all. The butterflies continue to fly equally in all directions. They do not cluster at the back of the cabin as if the ship's motion were leaving them behind. The fish swim just as easily toward the bow as toward the stern. The drops fall straight into the container, not shifted to one side. The smoke still rises upward. No internal experiment reveals the ship's motion. You cannot tell from anything happening inside that closed cabin whether you are moving at 10 knots, 20 knots, or standing still at anchor. This was radical. The natural assumption would be that motion is something real, something detectable, something that affects how things behave. If the ship is moving, surely the butterflies would have trouble keeping up. Surely the drops would fall at an angle. Surely something would reveal the motion. Galileo showed that this assumption is wrong for uniform motion. The physics inside the cabin is identical whether the ship moves or not. Think about what this means for the definition of motion itself. If no experiment inside a closed system can detect uniform motion, then what does it mean to say the system is moving? Moving relative to what? The dock? The ocean floor? The center of Earth? Each of these reference points gives a different answer, and Galileo's thought experiment suggests that none of them is physically privileged. There is no experiment inside the ship that will tell you which answer is correct. This is the seed that eventually grew into special relativity. Galileo planted it nearly 3 centuries before Einstein, simply by thinking carefully about what happens in a moving cabin. The principle has been tested countless times. Every time you fly in an aeroplane at cruising altitude and speed, you experience it directly. The coffee pours normally. You can walk up and down the aisle without difficulty. A dropped object falls straight down. Nothing inside the aeroplane reveals that you are moving at hundreds of miles per hour. The physics is the same as if you were on the ground. Galileo understood this in 1632, working it out through thought experiments and careful reasoning. The fact that we can still fly in aeroplanes and have the same experience he described centuries before powered flight existed shows how deeply he grasped the nature of motion. Let me fast forward to 1687, when Isaac Newton published his Principia and formalized classical mechanics. Newton's laws of motion worked beautifully. They explained how objects accelerate under forces, how planets orbit the sun, how cannonballs arc through the air. They unified terrestrial and celestial mechanics in a single mathematical framework. Newton understood Galileo's principle of relativity. His laws work the same in any inertial frame, meaning any frame moving in a straight line at constant speed. Whether you apply Newton's laws in a stationary laboratory or in a smoothly gliding train, you get the same physics. Yet Newton also introduced the concept of absolute space, a fixed background against which all motion could, in principle, be measured. This was partly mathematical convenience and partly philosophical commitment. Debates about whether absolute space was necessary or merely hypothetical continued for centuries. The question seemed abstract until the 19th century, when physicists began to think seriously about light. Light travels extraordinarily fast, approximately 299,792,458 meters per second in vacuum. Physicists in the 1800s assumed that light, like sound, must travel through some medium. Sound travels through air. Water waves travel through water. What did light travel through? They called this hypothetical medium the luminiferous ether, an invisible substance permeating all of space. If the ether existed and was at rest in some absolute sense, then Earth's motion through the ether should be detectable. As Earth orbits the Sun at nearly 30 kilometers per second, light traveling in the direction of Earth's motion should behave differently from light traveling perpendicular to that motion, just as swimming with a river current differs from swimming across it. In 1887, Albert Michelson and Edward Morley set out to detect this motion through the ether. They built an interferometer of unprecedented precision, capable of detecting tiny differences in the speed of light along different directions. If the ether existed and Earth moved through it, their device would show the effect. The result shocked the physics community. There was no effect. Light traveled at the same speed in every direction they tested. Earth's motion through the supposed ether was undetectable. This was not a small, null result. The experiment was precise enough that it should have detected the expected effect many times over. The ether, if it existed, was hiding completely from measurement. Various explanations were proposed. Perhaps the ether was dragged along by Earth. Perhaps objects contracted in the direction of motion in just the right way too. Cancel the effect. These ad hoc explanations multiplied, but none was satisfying. The stage was set for a revolution. In 1905, a young physicist working at a patent office in Switzerland published a paper that would transform our understanding of space, time, and motion. His name was Albert Einstein, and the paper introduced what we now call special relativity. Einstein took a radical approach. Instead of trying to explain why the ether was undetectable, he proposed that there was no ether. Instead of treating the constancy of light speed as a puzzling anomaly, he elevated it to a fundamental principle. Special relativity rests on two postulates. The first postulate extends Galileo's principle. The laws of physics take the same form in all inertial reference frames. Not just mechanical laws, but all physical laws, including the laws governing light and electromagnetism. The second postulate states that the speed of light in vacuum is the same for all inertial observers, regardless of the motion of the light source or the observer. These two postulates sound almost innocuous, but their consequences are revolutionary. Let me describe the Michelson-Morley experiment in more detail, because it was one of the most important null results in the history of science. The experiment used an instrument called an interferometer. A beam of light was split into two perpendicular beams that traveled along two arms of equal length, bounced off mirrors, and returned to recombine. When the beams recombined, they created an interference pattern, alternating bright and dark bands that depended on whether the waves were in phase or out of phase when they met. The key insight was that if Earth were moving through a stationary ether, the speed of light would differ along different directions. Light traveling along the direction of Earth's motion would have to fight against the ether on one leg of its journey and get a boost from the ether on the return leg. Light traveling perpendicular to Earth's motion would not experience this effect in the same way. These differences in light speed would cause the two beams to arrive back at the recombination point slightly out of sync, shifting the interference pattern in a detectable way. Michelson and Morley mounted their interferometer on a massive stone slab floating in a trough of mercury, which allowed them to rotate the apparatus smoothly and check for direction-dependent effects. They performed measurements throughout the day and at different times of year to account for Earth's changing motion around the Sun. The expected effect was well within the sensitivity of their apparatus. Earth orbits the Sun at about 30 kilometers per second, which would produce a measurable shift in the interference pattern if the ether existed. They found no effect. No matter which direction they pointed the interferometer, no matter what time of day or year they made their measurements, the speed of light was the same in all directions. This was deeply puzzling. If there were a medium through which light traveled, and if Earth moved through that medium, there should have been a detectable difference. The absence of any effect meant either that the ether did not exist, or that something extremely strange was happening. Various physicists proposed explanations. Hendrik Lorentz and George Fitzgerald independently suggested that objects contract in the direction of motion through the ether, by exactly the amount needed to cancel the expected effect. This length contraction would hide the motion through the ether from any measurement. The Lorentz-Fitzgerald contraction was mathematically successful at explaining the null result, but it was ad hoc. It assumed a physical contraction specifically designed to produce the observed outcome, without providing a deeper explanation for why such contraction would occur. Einstein took a different approach. Instead of trying to save the ether with compensating effects, he simply accepted the null result at face value and built a new theory on it. If the speed of light is the same for all observers, regardless of their motion, then that invariance is a fundamental principle, not an anomaly to be explained away. From that principle, combined with the relativity of motion from Galileo's insight, Einstein derived all the effects of special relativity: time dilation, length contraction, relativity of simultaneity, the famous E equals mc squared. The length contraction that Lorentz and Fitzgerald proposed as an ad hoc fix turned out to be a real effect. But it was not a physical compression of matter moving through ether. It was a consequence of how space and time are related, arising naturally from the geometry of spacetime. The Michelson-Morley experiment did not directly prove special relativity, but it removed one of the main obstacles to accepting it. If light did travel through an ether at different speeds, depending on direction, relativity would be violated. The null result showed that the speed of light really is constant, clearing the way for Einstein's radical proposal. Think about what the second postulate means. Imagine you are standing still while a spaceship zooms past you at half the speed of light. The spaceship shines a flashlight forward. How fast does the light travel? In everyday experience, you would expect the light to travel at the speed of the flashlight beam plus the speed of the ship, just as a ball thrown forward from a moving car travels faster relative to the ground than relative to the car. If the ship moves at half the speed of light, and the flashlight beam travels at the speed of light relative to the ship, you might expect the beam to travel at 1.5 times the speed of light relative to you. Special relativity says no. The light travels at exactly the speed of light relative to you, the same speed it has relative to the spaceship. both you and the spaceship pilot measure the same speed for that light beam, even though you are moving relative to each other at enormous velocity. This seems impossible. How can both observers measure the same speed for the same light beam when they are moving relative to each other? The answer is that space and time themselves behave differently than our intuitions suggest. For both observers to measure the same speed of light, something else must give. What gives is our everyday assumptions about time and distance. Time dilation is one consequence. Time passes at different rates in different reference frames. A clock moving relative to you ticks more slowly than an identical clock at rest relative to you. This is not an illusion or a measurement error. It is a fundamental feature of how space-time works. Length contraction is another consequence. Objects moving relative to you are shorter along the direction of motion than identical objects at rest relative to you. A spaceship zooming past you is literally shorter in your reference frame than it is in the reference frame of someone aboard the ship. The relativity of simultaneity is the deepest consequence of all. In special relativity, different inertial observers slice space-time into nows differently. Events that are simultaneous in one reference frame are not simultaneous in another reference frame, moving relative to the first. This is not a matter of perception or signal delay. It is a built-in feature of the theory. This is the part that still amazes me, even after years of studying this. Two observers can disagree about the order of events, about which event happened first, and both can be correct within their own reference frames. There is no absolute now that all observers share. Simultaneity is relative. Let me put this in perspective with a concrete example. Suppose two lightning bolts strike the ground, one to your east and one to your west, at what you perceive as exactly the same instant. According to you, the events are simultaneous. Now consider an observer on a train moving eastward past you at high speed at the moment the lightning strikes. Because of the way light, signals, and relative motion combine in special relativity, this observer will conclude that the eastern lightning bolt struck first. The events that were simultaneous for you are not simultaneous for the train passenger. Neither of you is wrong. Both descriptions are physically correct within their respective reference frames. There is no absolute answer to which lightning bolt struck first. This is what Galileo's insight becomes when you take it seriously and extend it to light and electromagnetism. Motion is relative. Rest is relative. Even simultaneity is relative. There is no fixed background, no absolute space, no universal now against which all observers can agree. Einstein did not just refine our understanding of motion, he transformed our understanding of space and time themselves. Let me explore the consequences of special relativity in more detail, because the implications reach far beyond abstract physics. Time dilation means that time passes at different rates in different reference frames. A clock moving relative to you ticks more slowly than an identical clock at rest relative to you. This is not a malfunction of the moving clock. It is not an illusion or a measurement error. Time itself, the fundamental progression that governs all physical processes, runs at different rates depending on relative motion. This has been measured directly. In 1971, physicists flew atomic clocks on commercial airplanes around the world, eastward and westward, while identical clocks remained on the ground. When the flying clocks were compared to the ground clocks, they differed by exactly the amount predicted by relativity, accounting for both their motion and their altitude. The differences were tiny, measured in nanoseconds, but they were real and exactly as predicted. Time dilation is not a theoretical curiosity. It is a measurable feature of the physical world. The GPS satellites that your phone uses for navigation experience time dilation. They orbit at high speed, which makes their clocks tick slightly slower than ground clocks due to special relativistic time dilation. They also orbit at high altitude, where gravity is weaker, which makes their clocks tick slightly faster than ground clocks due to general relativistic effects. The net effect is that GPS satellite clocks run faster than ground clocks by about 38 microseconds per day. If this were not corrected, GPS positions would drift by kilometers daily. The corrections are built into the system, a practical application of Einstein's theories that affects millions of people every day. Length contraction means that objects moving relative to you are shorter along the direction of motion than identical objects at rest relative to you. A spaceship zooming past at high speed is literally shorter in your reference frame than it is in the reference frame of the pilot aboard. This sounds strange, but it is a logical consequence of the two postulates of special relativity. If the speed of light is the same for all observers, and if the laws of physics are the same in all inertial frames, then space and time must be interconnected in ways that produce these effects. The relativity of simultaneity is perhaps the most counterintuitive consequence. Events that are simultaneous in one reference frame are not simultaneous in another reference frame, moving relative to the first. Imagine a train car with a light source at the center and detectors at both ends. The light source emits a flash. In the reference frame of someone on the train, the light travels equal distances to both ends and arrives simultaneously. Now consider someone standing on the platform as the train moves past. In their reference frame, the light still travels at the same speed, but the back of the train is moving toward where the light was emitted while the front is moving away. The light reaches the back detector first and the front detector second. Both observers are correct within their reference frames. The simultaneity of the light reaching the two detectors is not an absolute fact, but depends on the observer's state of motion. This is not a result of signal delays or measurement errors. It is a fundamental feature of space-time. Different inertial observers literally slice space-time into moments of now differently. There is no absolute present that all observers share. Special relativity applies to inertial frames, those moving in straight lines at constant speeds. What about acceleration? What about gravity? Einstein spent the next 10 years working on these questions, and in 1915 he published General Relativity, one of the most profound achievements in the history of physics. General relativity reframes gravity entirely. In Newton's picture, gravity is a force acting at a distance. The Sun exerts a gravitational pull on Earth across empty space, and that pull keeps Earth in orbit. The mechanism of this action at a distance was always somewhat mysterious, but Newton's equations worked so well that physicists accepted them anyway. Einstein proposed something radically different. In general relativity, gravity is not a force at all in the traditional sense. Instead, massive objects curve the geometry of space-time around them, and other objects follow paths through that curved geometry. Think of it this way. Imagine a heavy ball placed on a stretched rubber sheet. The ball creates a depression, curving the sheet around it. If you roll a marble across the sheet, the marble's path curves as it passes near the depression, not because the ball is pulling on it, but because the sheet itself is curved. This is an analogy, and like all analogies, it has limits, but it captures the essential idea. Massive objects curve space-time, and other objects move along the straightest possible paths through that curved space-time. These straightest possible paths are called geodesics. Here is the remarkable part. In general relativity, an object in freefall is following a geodesic. It is moving inertially, which means no force is acting on it. The apple falling from the tree is not being pulled by Earth's gravity in the general relativistic description. Instead, the apple is moving along a geodesic through curved space-time, the straightest path available to it. What we experience as the force of gravity is actually the ground accelerating upward to meet us. Standing on Earth's surface, you are not at rest. You are being accelerated upward by the ground pushing against your feet. That acceleration is what you feel as weight. An astronaut in orbit feels weightless, not because gravity is absent, but because they are in freefall, following a geodesic, experiencing no acceleration. This is counterintuitive. We think of standing on solid ground as the natural state of rest, and falling as motion. General relativity inverts this. Free fall is the natural state of inertial motion. Standing on solid ground is actually acceleration. Pause for a moment and think about what that means. Right now, the floor beneath you is accelerating you upward at about 9.8 meters per second squared. Not in the sense of pushing you through space, but in the sense of preventing you from following your natural geodesic path through curved space-time. If the floor disappeared, you would begin following a geodesic, falling freely, experiencing no acceleration at all. This is why astronauts float in the International Space Station. The station is in orbit, which is a form of freefall. Everything inside the station, astronauts included, is following geodesics through space-time. And since everything is falling together, nothing feels any force. General relativity deepens the insight that rest is relative. In curved space-time, even the distinction between accelerated and inertial motion becomes local. What counts as a straight path, an inertial trajectory, depends on the curvature of space-time in your region. Let me explore the general relativistic picture in more detail, because the claim that gravity is geometry deserves careful explanation. In Newton's picture, gravity is a force. The Sun exerts a gravitational pull on Earth, and that pull accelerates Earth toward the Sun. The acceleration curves Earth's path into an elliptical orbit instead of a straight line. This picture works extremely well for most purposes. Newton's equations accurately describe planetary orbits, projectile motion, tides, and countless other phenomena. The picture of gravity as a force acting at a distance is intuitive and computationally powerful. Einstein's picture is different. In general relativity, massive objects curve the geometry of space-time around them. Other objects then move along the straightest possible paths through that curved geometry. What does it mean for space-time to be curved? Think about the surface of a sphere like Earth. If you try to draw a straight line on a sphere, you get what is called a great circle, like the equator or a line of longitude. These are the straightest paths available on a curved surface. They minimize distance between points, the way a straight line does on a flat surface. Now, imagine two people starting at the equator and walking due north, perfectly parallel to each other. On a flat surface, they would stay the same distance apart forever. On a sphere, they converge as they approach the North Pole. The curvature of the surface causes initially parallel paths to come together. This is what happens in curved space-time. Objects following geodesics, the straightest possible paths, appear to accelerate toward each other because the geometry of space-time is curved by nearby masses. Earth curves space-time around it. An apple falling from a tree is not being pulled by a force in the general relativistic picture. Instead, the apple is following a geodesic through curved space-time, the natural trajectory that requires no force to maintain. What we call gravity is actually the curvature of space-time, causing geodesics to converge. This leads to the remarkable conclusion that free fall is inertial motion. In Newtonian physics, an object in free fall is accelerating. Gravity is a force, and the object responds to that force by changing its velocity. An astronaut in orbit is being constantly accelerated toward Earth, even though they feel weightless. In general relativistic physics, an object in free fall is not accelerating. It is following a geodesic, the straightest possible path through curved space-time. No force acts on it. The astronaut in orbit feels weightless because no force acts on them. They are moving inertially through curved space-time. What about standing on solid ground? In Newton's picture, you are at rest, and gravity pulls you downward, but the ground pushes you upward with an equal force, so you remain stationary. In general relativity, standing on solid ground is not inertial. The ground is accelerating you upward by pushing against your feet. You feel weight because you are being accelerated, not because gravity is pulling you down. This might seem like a semantic distinction, but it has physical consequences. General relativity makes different predictions than Newtonian gravity in certain situations, and those predictions have been tested and confirmed. The precession of Mercury's orbit was one of the first confirmations. Newtonian gravity predicts that Mercury's elliptical orbit should precess slowly over time. But the observed precession was slightly larger than Newton predicted. General relativity accounts for the difference exactly. The bending of light by gravity was another early confirmation. Light passing near the Sun is bent by the Sun's mass. General relativity predicts twice as much bending as Newtonian gravity would suggest. Observations during solar eclipses confirmed the general relativistic prediction. Gravitational time dilation, the slowing of clocks in stronger gravitational fields, is another general relativistic effect that has been measured directly with atomic clocks at different altitudes. All of these effects confirm that general relativity is the correct description of gravity, at least at the scales and energies we can test. Gravity really is geometry, and what we experience as gravitational force is really the curvature of space-time. Let me bring this back to the question of how fast we are really moving, because now you can see why the question requires context. The question, how fast am I moving, only has meaning when you specify relative to what. Different reference frames give different answers, and physics treats all inertial frames as equally valid. There is no privileged frame that tells you your true speed. That said, there are natural and useful reference frames that we can consider, each revealing a different layer of our motion through the cosmos. Start with Earth's rotation. Earth spins on its axis, completing one rotation every 23.934 hours, which is the sidereal day. The equatorial radius of Earth is 6,378.137 kilometers, which means the circumference of the equator is about 40,075 kilometers. Dividing circumference by rotation period gives the rotation speed at the equator, approximately 0.465 kilometers per second, or about 1,674 kilometers per hour, which comes to roughly 1,040 miles per hour. If you live at the equator, you are moving eastward at over 1,000 miles per hour just from Earth's rotation. If you live at higher latitudes, your rotational speed is lower because you are closer to the axis of rotation, but it is still substantial. In one day, Earth's rotation carries you through about 40,185 kilometers relative to the axis of rotation, nearly the full circumference of the planet. This motion is completely imperceptible. You feel nothing, because you, the air around you, and everything in your environment are all rotating together. Galileo's principle applies. Uniform motion cannot be detected from within. There is no experiment you can do inside a sealed room that will tell you Earth is rotating. Actually, that is not quite true. Earth's rotation is not uniform in the relativistic sense, because it involves constant change of direction. Very precise instruments like Foucault pendulums and ring laser gyroscopes can detect Earth's rotation. The physics is subtle, but the rotation is measurable by sufficiently sensitive equipment. Now add Earth's orbit around the Sun. Earth orbits the Sun at a mean speed of approximately 29.8 kilometers per second, which is about 107,280 kilometers per hour, or roughly 66,661 miles per hour. This is enormously faster than our rotation speed. In one day, Earth's orbital motion carries us approximately 2,574,720 kilometers along our path around the Sun, a distance almost 7 times greater than the Earth-Moon distance. Again, this motion is imperceptible in ordinary experience. We cannot feel ourselves moving around the Sun, any more than passengers on a smooth airplane feel themselves moving at 600 miles per hour. The motion is uniform on timescales of hours or days, and we are moving together with everything around us. Now consider the Sun's motion around the Milky Way galaxy. Our solar system is located in one of the spiral arms of the Milky Way, orbiting the galactic center at roughly 220 to 230 kilometers per second, depending on which measurements and models you use. That translates to approximately 792,000 to 828,000 kilometers per hour, or about 492,000 to 515,000 miles per hour. At this speed, our solar system travels between 19 and 20 million kilometers every single day, a distance about 50 times greater than the Earth-Moon separation. One complete orbit around the Milky Way takes approximately 230 million years, a period sometimes called a cosmic year. The last time our solar system was in this part of its galactic orbit, dinosaurs had not yet appeared on Earth. Think about that for a moment before we continue. Let me walk through the calculation of our daily motion more carefully, because the numbers deserve attention. Start with Earth's rotation. The equatorial radius of Earth is 6,378.137 kilometers, which is about 3,963 miles. The circumference at the equator is therefore 2 times pi times the radius, which works out to about 40,075 kilometers, or roughly 24,901 miles. Earth completes one rotation in one sidereal day, which is about 23.934 hours. This is slightly shorter than the 24-hour solar day, because Earth is also orbiting the Sun, so it needs to rotate a bit more than 360 degrees between successive noons. Dividing the equatorial circumference by the sidereal day gives the rotation speed at the equator, approximately 0.4651 kilometers per second, which is about 1,674 kilometers per hour, or roughly 1,040 miles per hour. If you live at the equator, you complete one full circuit around Earth's axis every sidereal day, traveling about 40,000 kilometers. This is equivalent to flying around the world every day, carried by the planet's rotation. At higher latitudes, the circumference of your daily circle is smaller because you are closer to the axis of rotation. At latitude 45 degrees, for example, your daily circuit is about 28,000 kilometers. At latitude 60 degrees, it is about 20,000 kilometers. At the poles, you simply rotate in place, covering no distance at all relative to the axis. Now add Earth's orbit around the Sun. Earth's mean orbital speed is approximately 29.8 kilometers per second, which is about 107,280 kilometers per hour, or roughly 66,661 miles per hour. This is about 64 times faster than our equatorial rotation speed. In one day, Earth's orbital motion carries us approximately 29.8 kilometers per second times 86,400 seconds per day, which equals about 2,574,720 kilometers, or roughly 1.6 million miles. To put this in perspective, the Earth-Moon distance averages about 384,400 kilometers. Our daily orbital travel is about 6.7 times the Earth-Moon distance. Every 6 days, we travel roughly as far around our orbit as the Moon is from Earth in a straight line. Now add the Solar System's orbit around the Milky Way. The Sun orbits the galactic center at somewhere between 220 and 230 kilometers per second, depending on the measurement method and the assumed distance to the galactic center. Using 225 kilometers per second as a middle estimate, this works out to about 810,000 kilometers per hour, or roughly 503,000 miles per hour. In one day, this carries us approximately 19,440,000 kilometers, or about 12 million miles. This is roughly 50 times the Earth-Moon distance. Finally, add our motion relative to the CMB. At 369 kilometers per second, we travel approximately 31,881,600 kilometers per day relative to the cosmic background radiation, or about 19.8 million miles. This is roughly 83 times the Earth-Moon distance. The Earth-Moon distance provides a useful benchmark. We are all familiar with the Moon in the sky and have some intuition about how far away it is. Using that distance as a measuring stick, our daily cosmic journey becomes more tangible. 83 Earth-Moon distances every day, accumulated while you go about your ordinary life, completely unaware of the motion. Let me put our cosmic motion in perspective with some comparisons that might help you feel the scale. Our daily travel relative to the CMB, roughly 31.9 million kilometers, is about 83 times the average distance from Earth to the Moon. The Moon orbits Earth at a mean distance of approximately 384,400 kilometers, a distance you could fit our daily cosmic travel into 83 times over. Think about the Apollo missions. It took the astronauts about 3 days to travel from Earth to the Moon. In those same 3 days, traveling at 369 kilometers per second relative to the CMB, you would cover about 95.6 million kilometers, roughly 250 times the Earth-Moon distance, without moving a muscle. In 1 week, your CMB relative travel accumulates to about 223 million kilometers. That is greater than the distance from Earth to Mars at their closest approach, which occurs every couple of years when the planets are on the same side of the Sun. In 1 month, your CMB relative travel is roughly 957 million kilometers, greater than the distance from Earth to Jupiter when Jupiter is closest to us. In 1 year, you traverse approximately 11.6 billion kilometers relative to the CMB. That is roughly 77 times the distance from Earth to the Sun, or about 78 astronomical units. None of this motion is perceptible. You feel nothing, because you are moving with everything around you, because there is no fixed background against which your motion produces resistance or sensation. Let me compare these speeds to things you might be more familiar with. The fastest commercial aircraft, the now retired Concorde, cruised at about 2,180 kilometers per hour, roughly Mach 2.04, just over twice the speed of sound. Earth's rotation at the equator, 1,674 kilometers per hour, is about 77% of the Concorde's cruising speed. You are rotating almost as fast as that supersonic jet flew, just by standing on the equator. The International Space Station orbits Earth at about 28,000 kilometers per hour, which is roughly 7.7 kilometers per second. Earth's orbital speed around the Sun, 107,280 kilometers per hour, is nearly 4 times faster than the ISS. The fastest human-made object ever launched is the Parker Solar Probe, which will eventually reach speeds of about 700,000 kilometers per hour as it dives close to the Sun, using the Sun's gravity to accelerate. Our solar system's speed around the Milky Way, roughly 800,000 kilometers per hour, is faster than even the Parker Solar Probe will achieve. Our speed relative to the CMB, roughly 1.3 million kilometers per hour, is about twice as fast as our galactic orbital speed and almost twice as fast as the Parker Solar Probe's eventual maximum speed. These numbers are difficult to grasp intuitively, and that difficulty is itself informative. Our intuitions about speed are calibrated to everyday experiences: walking, driving, flying in airplanes. Cosmic speeds operate on entirely different scales, and our intuitions simply do not reach that far. What makes these speeds remarkable is not just their magnitude, but the fact that we can measure them at all. The dipole in the CMB, caused by our motion through the cosmic background radiation, was detected by satellites designed and built by humans, orbiting a planet that is itself in constant motion, measuring light that has been traveling for over 13 billion years. The precision required for these measurements is extraordinary. The temperature variations in the CMB are measured in millionths of a degree. The dipole signal, caused by our motion, is a variation of about 0.003 degrees, which we can detect and interpret correctly. These speeds I have been listing are measured in different reference frames: Earth's rotation relative to its axis, Earth's orbit relative to the Sun, the Sun's orbit relative to the galactic center. The frames are nested inside each other, and the velocities point in different directions at different times. You might wonder whether there is some ultimate reference frame, some cosmic background against which we can measure our total motion through the universe. Physics tells us there is no absolute rest frame in the sense of a privileged frame dictated by the laws of nature. all inertial frames are equally valid for describing physics. That said, there is a natural reference frame that arises from observation rather than theory: the rest frame of the cosmic microwave background. The cosmic microwave background, or CMB, is radiation left over from the early universe, light that has been traveling through space for over 13 billion years. This ancient light fills all of space almost uniformly. In every direction you look, you see this faint glow of microwave radiation at a temperature of about 2.7 degrees above absolute zero. When you measure the CMB very precisely, you find that it is not perfectly uniform. There is a dipole pattern. The CMB is slightly warmer in one direction of the sky and slightly cooler in the opposite direction. This dipole is exactly what you would expect if we were moving through the CMB at high speed. The light ahead of us is blue-shifted, appearing slightly warmer, while the light behind us is red-shifted, appearing slightly cooler. By measuring this dipole, we can determine our velocity relative to the CMB. The solar system moves at approximately 369 kilometers per second relative to the CMB rest frame, in a direction roughly toward the constellation Leo. At 369 kilometers per second, we traverse about 31.9 million kilometers every day, which is roughly 83 times the mean distance from Earth to the Moon, that familiar 384,400 kilometers or so that separates us from our nearest celestial neighbor. This is the closest thing physics offers to an answer to how fast are we really moving? Not because the CMB frame is physically privileged, but because it provides an observational anchor. In the CMB rest frame, the background radiation looks nearly isotropic. An observer at rest relative to the CMB would see the ancient light coming from all directions at nearly the same temperature. We are not at rest in that frame. We are moving at 369 kilometers per second. The motion goes deeper still. Our galaxy, the Milky Way, is part of a larger structure called the local group, which includes the Andromeda Galaxy and several dozen smaller galaxies. The local group as a whole moves relative to the CMB at approximately 627 kilometers per second in a direction toward the constellations Centaurus and Hydra. This motion is related to large-scale structures in the universe. In that direction lies a massive concentration of matter, sometimes called the Great Attractor, located roughly 40 to 50 megaparsecs away, which translates to about 120 to 150 million light-years. The gravitational influence of this and other large structures contributes to our motion relative to the CMB. At 627 kilometers per second, the local group traverses about 54 million kilometers every day relative to the CMB frame. I want to be clear about something important here. You cannot simply add these speeds together to get a single total speed. The velocities point in different directions, and those directions change continuously as Earth rotates, orbits the Sun, and accompanies the Sun around the galaxy. The proper way to combine velocities in relativity is more complex than simple addition. The CMB velocity of 369 kilometers per second for our solar system is a single clean number that provides a useful reference. It is Our velocity relative to the ancient light filling the universe, measured as a temperature asymmetry in the cosmic background radiation. Let me explore our motion relative to the CMB in more detail, because it reveals something fascinating about the large-scale structure of the universe. The CMB dipole tells us that our solar system moves at about 369 kilometers per second relative to the cosmic background radiation. This motion has a specific direction, roughly toward the constellation Leo. When astronomers analyzed the motion further, they found that the Sun's velocity is actually composed of multiple contributions. The Sun orbits the Milky Way center, so some of our velocity relative to the CMB comes from that galactic motion. The Milky Way itself moves relative to the local group barycenter, and the local group as a whole moves relative to the CMB. Decomposing these motions, astronomers found that the local group, the collection of galaxies that includes the Milky Way and Andromeda, moves at approximately 627 kilometers per second relative to the CMB. This is a significant velocity, even by cosmic standards. The direction of this motion points toward a region of the sky near the constellations Centaurus and Hydra. Something in that direction appears to be pulling the local group toward it. That something is often called the Great Attractor. Located roughly 40 to 50 megaparsecs away, which translates to about 120 to 150 million light-years, it represents a massive concentration of matter that influences the motion of galaxies over an enormous volume of space. The Great Attractor is not a single object, but a region of enhanced galaxy density. Behind it lies an even larger structure called the Shapley supercluster. The combined gravitational influence of these massive structures contributes to our motion through the universe. At 627 kilometers per second, the local group traverses about 54 million kilometers every day relative to the CMB. In a year, that accumulates to roughly 20 billion kilometers, a distance many times greater than the radius of the solar system. This cosmic flow is not something we can feel or directly perceive. We are moving with everything around us, falling together toward the same gravitational attractors, carried along by the large-scale dynamics of the universe. What we can detect is the dipole in the CMB, the asymmetry in the temperature of the background radiation caused by our motion through it. Light ahead of us is blue-shifted and appears slightly warmer. Light behind us is red-shifted and appears slightly cooler. This pattern encodes our velocity relative to the cosmic rest frame. The remarkable thing is that we can measure this. Satellites like COBE, WMAP and Planck have mapped the CMB with extraordinary precision, detecting temperature variations of millionths of a degree. From these measurements, we can extract our cosmic velocity to high accuracy. This turns an abstract philosophical question into a concrete measurement. Are we moving through the universe? In what sense? Relative to what? The CMB provides an observational answer, a rest frame defined not by theory, but by measurement. Let me turn to one of the strangest predictions of general relativity, an effect so subtle that it took decades of technological development before we could measure it: frame dragging. In 1918, two physicists named Joseph Lense and Hans-Thirring worked out a prediction of Einstein's general relativity. They showed that a rotating massive object does not just curve space-time around it, it actually drags space-time along with its rotation, twisting the local geometry like a spoon slowly stirring honey. This effect is sometimes called the Lense-Thirring effect, and it belongs to a broader category of effects called gravitomagnetism, because the mathematics resembles the way moving electric charges create magnetic fields. Imagine space-time as a kind of fabric. A massive object creates depression in the fabric, curving it. If the massive object is rotating, it does not just create a depression, it also imparts a swirl, a slight twist to the fabric in the direction of rotation. This swirl affects everything nearby. Objects in orbit around the rotating mass do not just follow curved paths due to the mass. Their orbits are also twisted slightly in the direction of the mass's rotation. The effect is tiny, but it is real, and it has been measured. Around Earth, frame dragging is extremely small. The predicted effect on satellite orbits is only about 31 to 33 milliarcseconds per year. To put that in perspective, there are 3,600 arcseconds in a degree and 360 degrees in a full circle. An effect of 31 milliarcseconds per year means the orbital plane of a satellite twists by a few hundredths of an arcsecond annually, a shift so small it is almost undetectable. In terms of physical distance, for a satellite at about 12,000 kilometers altitude, the frame dragging effect amounts to less than 2 meters of orbital shift per year. 2 meters per year. That is the signal physicists set out to detect. Measuring such a tiny effect requires extraordinary precision. The experiments that have confirmed frame dragging around Earth represent some of the most delicate measurements ever performed in physics. The first significant measurement came in 2004, when researchers published results using satellite laser ranging. This technique tracks satellites with exquisite precision by bouncing laser pulses off reflectors mounted on the spacecraft. The satellites used were Lagios and Lagios 2, laser-ranged satellites with orbits specifically chosen to be sensitive to relativistic effects. By tracking these satellites over years and carefully accounting for all other influences on their orbits, researchers were able to isolate the tiny frame-dragging signal. The 2004 Nature paper by Ciuffolini and Pavlis reported a measurement consistent with General Relativity's prediction, confirming frame dragging at roughly the 10% level of precision. This was a remarkable achievement. The signal they were looking for was buried in a much larger background of other effects: irregularities in Earth's gravitational field, atmospheric drag, solar radiation pressure, and dozens of other perturbations. Extracting the frame-dragging signal required sophisticated modeling and years of observations. Let me explain frame dragging in more technical detail, because the physics is fascinating even though the effect around Earth is small. In electromagnetism, moving electric charges create magnetic fields. A current flowing through a wire produces a magnetic field that circles the wire. This is the principle behind electromagnets, electric motors, and generators. General relativity has an analogous effect. moving mass energy creates a gravitational effect similar to magnetism, called gravitomagnetic fields. Just as a current of electric charge produces magnetic field, a current of mass produces a gravitomagnetic field. A rotating mass like Earth can be thought of as a circulation of mass energy. The rotation creates gravitomagnetic effects that twist the geometry of space-time around the rotating object. This twist affects how nearby objects move. An object orbiting a rotating mass does not just orbit due to the mass's gravity. Its orbital plane is also dragged slightly in the direction of the mass's rotation. For Earth, the predicted effect is tiny. The orbital planes of satellites, like LAGEOS, precess by about 31 to 33 milliarcseconds per year due to frame dragging. This is on top of much larger precession effects due to other causes, mainly Earth's equatorial bulge. To understand how small 31 milliarcseconds is, consider that a full circle is 360 degrees. Each degree contains 60 arc minutes, and each arc minute contains 60 arc seconds. So there are 1,296,000 arc seconds in a full circle, or about 1.3 million arc seconds. 31 milliarcseconds is 0.031 arc seconds. At the altitude of LAGEOS, roughly 12,000 kilometers, this corresponds to an orbital shift of less than 2 meters per year. Extracting this tiny signal from the much larger background of other effects is extraordinarily difficult. Earth's gravitational field is not perfectly spherical. The planet bulges at the equator due to its rotation, and there are mountains, ocean basins, and density variations that create gravitational anomalies. These effects on satellite orbits are thousands of times larger than the frame dragging effect. To measure frame dragging, researchers must model all these other effects precisely and subtract them from the observed orbital behavior. What remains, after all other effects are accounted for, is the frame dragging signal. The LAGEOS satellites were chosen for this measurement because they are extraordinarily simple objects, solid spheres covered with reflectors, with no moving parts or propulsion systems. Their orbits are affected almost entirely by gravity, with minimal perturbations from atmospheric drag, solar radiation pressure, or other non-gravitational effects. Even so, the analysis is challenging. The results from satellite laser ranging confirm frame dragging at roughly the 10% level of precision, consistent with general relativity, but with uncertainties that researchers continue to work on reducing. Gravity Probe B took a different approach. Instead of measuring orbital precession, it measured the precession of gyroscopes carried in a satellite. A gyroscope maintains its orientation in space due to conservation of angular momentum. If spacetime were flat and there were no frame dragging effect, a gyroscope in orbit around Earth would maintain a constant orientation relative to the distant stars. General relativity predicts two effects on orbiting gyroscopes. Geodetic precession, caused by the curvature of space-time around Earth's mass, should cause the gyroscope axis to precess by about 6,606 milliarc-seconds per year. Frame dragging precession, caused by Earth's rotation dragging spacetime, should cause an additional precession of about 39 milliarc-seconds per year in a different direction. By measuring the precession of 4 gyroscopes over more than a year, Gravity Probe B could test both predictions. The mission succeeded in confirming geodetic precession with high precision. The frame dragging measurement was more challenging due to unexpected torques from electrostatic patches on the gyroscope surfaces. But after careful analysis, the results were consistent with general relativity at roughly the 20% level. An even more ambitious experiment was Gravity Probe B, a NASA mission decades in the making. The concept was elegant. Place a satellite in polar orbit around Earth carrying extremely precise gyroscopes. These gyroscopes, once spinning, should maintain their orientation fixed relative to the distant stars, unless some force or effect causes them to precess. General Relativity predicts 2 effects on orbiting gyroscopes. The first is geodetic precession, caused by the curvature of spacetime around Earth's mass. The second is frame dragging precession, caused by Earth's rotation twisting spacetime around itself. The geodetic effect is larger, about 6,606 milliarc-seconds per year for Gravity Probe B's orbit. The frame dragging effect is much smaller, predicted at about 39.2 milliarc-seconds per year. The mission aimed to measure both. Building gyroscopes precise enough to detect these effects was an engineering challenge unlike almost any other. The gyroscopes needed to be so stable that their drift rates could be measured to fractions of a milliarc-second per year. Normal gyroscopes drift far too much. The Gravity Probe B team had to invent new technologies. The gyroscopes were nearly perfect spheres of fused quartz, coated with a thin layer of niobium to make them superconducting at cryogenic temperatures. When cooled to near absolute zero and set spinning, these spheres became some of the roundest objects ever manufactured, with surface variations of less than 40 atoms. The satellite carried 4 of these gyroscopes, oriented in different directions to check for systematic errors. A telescope locked onto a guide star provided the reference direction against which the gyroscope's precession was measured. Gravity Probe B launched in 2004 and operated for over a year, collecting data on the gyroscope's behavior. The results were published in 2011 in Physical Review Letters. The geodetic precession was measured with high precision, matching the predicted value beautifully. The frame dragging measurement was more challenging due to unexpected torques that arose from electrostatic patches on the gyroscope surfaces. But after careful analysis, the team reported a frame dragging drift rate of negative 37.2 milliarc-seconds per year, plus or minus 7.2 milliarc-seconds per year, compared to the predicted negative 39.2 milliarc-seconds per year. This is a roughly 20% precision measurement, limited by the unexpected systematic effects rather than by the experimental concept. The result is consistent with general relativity. I find it remarkable that engineers built gyroscopes so stable that milliarc-seconds per year drifts became measurable. This is precision at the edge of what is technologically possible, achieved to test a prediction Einstein made a century ago. The frame dragging effect around Earth is tiny, barely detectable with our best instruments, yet it exists. Earth's rotation genuinely twists space-time around it, and that twist affects the motion of satellites and gyroscopes in measurable ways. In environments with more extreme rotation, frame dragging becomes much stronger. Around a spinning black hole, the effect can be enormous, dragging space-time around with the black hole's rotation and affecting how matter falls in and how energy is extracted. Around Earth, the effect is a whisper, a shift of less than 2 meters per year in satellite orbits. Detecting that whisper took satellites, lasers, cryogenic gyroscopes, and decades of work. The fact that we succeeded is a testament to human ingenuity and persistence. Let me reflect on the extraordinary precision that modern physics achieves in measuring these effects. The Michelson-Morley interferometer could detect changes in light travel time of about a billionth of a second. This precision, unprecedented in 1887, was enough to conclusively show that no ether wind existed at the level they could measure. Gravity probe B measured gyroscope drifts of fractions of a milli-arcsecond per year. To put this in perspective, imagine looking at a circle and dividing it into 360 degrees. Each degree contains 3,600 arcseconds. A milli-arcsecond is 1,000th of an arcsecond. The effect gravity probe B measured was tens of milli-arcseconds per year, an angular change so tiny that it takes centuries to accumulate to a single degree. The satellite laser ranging that measures frame dragging with LAGEOS tracks these satellites to centimeter precision from thousands of kilometers away. Laser pulses are fired from ground stations, bounce off reflectors on the satellites, and return. The round-trip time is measured with nanosecond precision. From millions of these measurements over years, researchers extract orbital parameters to extraordinary accuracy. These measurements push the limits of what technology can achieve. The gyroscopes in Gravity Probe B were the most perfect spheres ever manufactured at the time, with surface variations smaller than 40 atoms. The vacuum in the probe container was among the best ever achieved. The magnetic shielding protected the superconducting gyroscopes from external interference. Every potential source of error had to be identified and controlled. Unexpected effects, like the electrostatic patches that limited the frame dragging, measurement precision required years of analysis to understand and account for. This level of effort reflects the importance of testing fundamental physics. General relativity is one of the most successful theories in physics, confirmed by many independent observations. Yet, scientists continue to test it more precisely, looking for any deviation that might hint at new physics beyond Einstein. To date, general relativity has passed every test. The frame dragging measurements agree with predictions. Gravitational wave observations match the waveforms calculated from Einstein's equations. GPS satellites navigate with relativistic corrections and deliver positions accurate to meters. This success does not mean we stop testing. New technologies enable new measurements, more precise satellites, better gravity models, and advanced instruments continue to push the boundaries of what we can observe. The commitment to testing theoretical predictions, even when those predictions have been confirmed many times before, is what distinguishes science from mere belief. We do not accept general relativity because Einstein was a genius. We accept it because experiments confirm its predictions, again and again, with increasing precision. Each new confirmation strengthens our confidence. Each null result, when we search for deviations, tells us that Einstein's theory holds at yet another level of precision. The frame dragging measurements are part of this ongoing process, confirming relativity in a regime where the effects are extraordinarily small and the measurements extraordinarily difficult. Let me discuss where the science currently stands and what remains to be done. Frame dragging around Earth is considered experimentally confirmed, though the precision is not yet at the level physicists would ideally like. The Lagios measurements achieved roughly 10% precision. Gravity probe B achieved roughly 20% precision on the frame dragging channel, limited by unexpected systematic effects. Work continues to refine these measurements. Additional satellites, like LARES, combined with improved models of Earth's gravitational field from missions like GRACE and GOCE, allow researchers to reduce uncertainties and cross-check results. One of the major challenges is separating the frame dragging signal from the effects of Earth's complex gravitational field. Earth is not a perfect sphere. It has an equatorial bulge, mountain ranges, ocean basins, and variations in density that create a complicated gravitational pattern. These effects on satellite orbits are much larger than the relativistic effects, so they must be modeled with extreme precision before the frame dragging signal can be extracted. Non-gravitational perturbations also complicate the analysis. Atmospheric drag, solar radiation pressure, thermal effects, all of these can shift satellite orbits in ways that must be accounted for. The open questions are less about whether frame dragging exists, which is now well established, and more about achieving higher precision measurements and understanding the systematic uncertainties in each experimental approach. Let me step back and offer some analogies that might help you visualize what we have discussed. Think about a treadmill. You can be at rest relative to the treadmill belt, while the belt carries you backward relative to the room. Two reference frames, two different answers to whether you are moving. Both are correct within their respective frames. An airport moving walkway offers a similar example. Two people can have different speeds relative to the terminal, while both are at rest relative to the walkway surface. Ask, how fast is that person moving? And the answer depends on what you measure relative to. For frame dragging, think of a spoon slowly stirring honey. The honey near the spoon gets dragged along with the rotation, swirling in the direction the spoon is turning. Spacetime near a rotating mass behaves similarly, though the effect is vastly smaller and the analogy has limits. These analogies are imperfect, as all analogies are, but they capture the essential ideas. Motion is relative. Rest is relative. Even the local definition of an inertial direction gets twisted by rotating masses. What makes this profound is that these are not just different ways of describing the same underlying reality. In relativity, There is no single underlying reality independent of reference frames. The choice of frame affects what you measure, and different observers will get different results that are all equally valid descriptions of the physics. This is not relativism in the philosophical sense. The laws of physics are the same for all observers. The predictions of relativity can be tested and have been confirmed repeatedly. What is relative is the description. Speeds, times, lengths, and simultaneity are frame-dependent rather than absolute. Let me discuss what frame dragging means for our understanding of motion and space. Frame dragging shows that even the local definition of which direction is not rotating gets influenced by nearby rotating masses. If you had a perfectly precise gyroscope far from any massive objects, its axis would define a direction fixed relative to the distant stars. Near a rotating mass, that definition gets twisted. This is profound. We tend to think of space as a passive stage on which events play out. Objects move through space, but space itself is just empty background, unchanging and uninvolved. General relativity tells us otherwise. Space, or more precisely space-time, is a dynamic entity that responds to the presence of matter and energy. Mass curves space-time. Rotation twists it. These effects are real and measurable. The frame-dragging effect around Earth is tiny, but around more extreme objects it becomes dominant. Near a spinning black hole, frame dragging is so strong that space-time itself is dragged around with the black hole's rotation. There is a region called the ergosphere, where space-time is dragged so rapidly that nothing, not even light, can remain stationary relative to the distant stars. Everything in the ergosphere must orbit in the direction of the black hole's rotation. This has implications for how matter falls into black holes and how energy can be extracted from them. The physics of accretion disks, jets, and other phenomena around spinning black holes depends critically on frame-dragging effects. Around neutron stars, frame dragging is also significant. Neutron stars are incredibly dense, with masses comparable to the Sun packed into spheres only tens of kilometers across. Their rapid rotation creates strong gravitomagnetic effects that affect the orbital behavior of matter around them. Earth's frame-dragging effect is a whisper compared to these extreme environments, but it arises from the same physics. The equations of general relativity describe both the tiny twist of space-time around our slowly rotating planet and the violent dragging around a rapidly spinning black hole. What I find remarkable is that we can measure the tiny effect here on Earth at all. The precision required to detect an orbital shift of less than 2 meters per year, buried in a background of much larger perturbations, pushes the limits of our technology. Let me also reflect on what all of this tells us about the nature of physical reality. We often think of physics as discovering facts about an objective world that exists independently of how we describe it. There is a world out there, and physics tells us what it is like. Relativity complicates this picture. The question, how fast is that object moving, does not have a single objective answer. Different reference frames give different answers, and physics treats all inertial frames as equally valid. This does not mean that anything goes, or that reality is subjective in some loose sense. The laws of physics are the same for all. observers. Experiments give consistent results. Predictions can be made and tested. What is relative is the description, the numbers we assign to quantities like speed, time intervals, and lengths. These numbers depend on the reference frame we choose, and different frames give different numbers. The underlying physical reality consists of events in space-time and the relationships between them. Different observers describe these events using different coordinate systems, but the events themselves and their space-time relationships are invariant. This is a sophisticated view of physical reality, one that took centuries to develop. It requires letting go of the intuition that motion is an intrinsic property of objects and accepting that motion is a relationship, always measured relative to something. The payoff is a theory of extraordinary power and precision, confirmed by countless experiments, built into technologies we use daily, and capable of predicting phenomena from GPS navigation to gravitational waves to the behavior of black holes. Let me explore what all of this means for how we understand the world. Our everyday intuition tells us that motion and rest are properties of objects. A car is moving or it is parked. A person is walking or standing still. These seem like facts about the objects themselves, independent of who is observing. Relativity tells us that motion and rest are not properties of objects, but relationships between objects. Whether something is moving depends on what you compare it to. There is no experiment you can do to determine your absolute motion, no measurement that will tell you how fast you are really moving through space itself, because space itself provides no fixed background. This is a deep revision of our ordinary concepts. We speak of objects moving as if motion were a quality they possess. Physics tells us this language is misleading. Motion is always motion relative to something, and different somethings give different answers. Think about what this means for the concept of being at rest. In everyday language, being at rest means not moving. You are at rest when you are sitting still, standing in place, lying in bed. But sitting still relative to what? Your chair? Earth's surface? The sun? The galactic center? The CMB? If rest is defined relative to a reference frame, and different frames give different answers, then there is no frame-independent fact of the matter about whether you are at rest. You are at rest in some frames and moving in others. And physics does not privilege any frame as the one that tells you the truth. This is what physicists mean when they say there is no absolute rest. The concept of rest, like the concept of motion, is frame-dependent. There is no experiment you can do inside a sealed room to determine whether you are truly at rest or truly moving. I remember when I first fully absorbed this idea, and it required letting go of intuitions that felt deeply natural. The sense that I am either moving or not moving, that there is a fact of the matter independent of how you describe it, is hard to shake. Relativity asks us to accept that this intuition is wrong. What remains is relationships. You are at rest relative to your chair. You are moving at 1,674 kilometers per hour relative to Earth's axis. You are moving at 369 kilometers per second relative to the CMB. These are all true statements about your state, and they do not contradict each other because they refer to different relationships. General relativity adds another layer. In curved spacetime, even the distinction between inertial and accelerated motion becomes local. What counts as a straight path depends on the curvature of spacetime in your region. Freefall is inertial motion, even though it looks like acceleration from the perspective of someone standing on the ground. Frame dragging adds yet another layer. The local definition of which direction is not rotating gets twisted by nearby rotating masses. The gyroscopes on Gravity Probe B measured this twist directly. The space-time around Earth is not just curved by Earth's mass, it is also dragged by Earth's rotation. All of these effects, time dilation, length contraction, relativity of simultaneity, space-time curvature, frame dragging, have been measured experimentally. They are not just theoretical possibilities, but confirmed features of how the physical world works. Let me discuss how relativity shows up in everyday situations that you might not have considered. Every time you ride in a car, train, or aeroplane, you experience Galileo's principle directly. You can pour a drink, write a note, or toss a ball up and catch it, all without any awareness of your vehicle's motion, as long as the motion is smooth and steady. The moment the vehicle accelerates, brakes, or turns, you feel it. Your body is pushed back into the seat during acceleration, pushed forward during braking, pushed sideways during turns. These are the effects of acceleration, which is detectable from within a closed system. Uniform motion, however, is invisible from inside. This is why passengers on a smoothly cruising aeroplane can walk around, eat meals, and behave almost exactly as they would on the ground. The aeroplane's 800 km/h speed does not affect the physics inside the cabin. This distinction between uniform motion and acceleration is at the heart of special relativity. Inertial frames, those in uniform motion, are all equivalent. Accelerated frames are different, and the principle of equivalence in general relativity relates acceleration to gravity. Consider the International Space Station. It orbits Earth at about 28,000 km/h, completing one orbit every 90 minutes. The astronauts inside are in continuous free fall, following a geodesic through curved space-time. They feel weightless, not because gravity is absent, but because they are in inertial motion. If the station were to fire its thrusters to accelerate, the astronauts would feel it immediately. They would be pushed in the direction opposite the acceleration, just as you are pushed back into your seat when a car accelerates. But during normal orbit with no thrust, they float freely. This weightlessness in orbit is often misunderstood. Many people think astronauts float because they are beyond Earth's gravity. In fact, gravity at the station's altitude is only about 10% weaker than at Earth's surface. The astronauts float because they are falling, constantly falling around Earth, following the curvature of space-time. The same physics that makes astronauts weightless makes you feel weight on the ground. Standing on Earth's surface, you are not in free fall. The ground is accelerating you upward, resisting your natural tendency to follow a geodesic. That upward acceleration is what you feel as weight. This is the general relativistic perspective, and it inverts our usual intuitions. We think of the ground as the natural state and falling as motion. Relativity tells us free fall is the natural state, the inertial motion through curved space-time, and standing on the ground is acceleration. The distinction matters because it affects precise measurements. Clocks at different altitudes run at different rates due to gravitational time dilation. Clocks in motion experience special relativistic time dilation. These effects are tiny at everyday speeds and ordinary gravitational fields, but they are real and measurable with sufficiently precise instruments. The network of satellites and ground stations that make up modern navigation and communication systems must account for these effects. Engineers who design and operate these systems use relativistic calculations routinely, not as exotic theory, but as practical necessity. Let me address some common misconceptions before we continue. One misconception is that relativity means anything goes, that all descriptions are equally valid in some loose sense that undermines objectivity. This is wrong. Relativity has precise rules. The laws of physics are the same in all inertial frames, and the predictions of the theory can be tested rigorously. What varies between frames are the descriptions, the numbers you assign to time intervals, lengths, and speeds. The underlying physics is the same. Another misconception involves faster-than-light motion. Some people hear about cosmic motions, galaxies receding at enormous speeds, and conclude that things are moving faster than light through space. This is not what happens. In relativity, any object's speed through local space is always less than the speed of light. The large recession speeds discussed in cosmology refer to metric expansion, the stretching of space itself, not motion through space. These are different concepts, and conflating them leads to confusion. A third misconception is that because rest is relative, our motion through space does not matter or is somehow not real. The motion is real in the sense that it has measurable consequences. Our motion relative to the CMB produces a measurable dipole in the cosmic background radiation. Our motion around the galaxy produces measurable stellar aberration and other effects. The relativity of motion does not mean motion is unreal. It means motion is a relationship rather than an intrinsic property. Let me return to the numbers once more, because they are worth dwelling on. Right now, you are participating in multiple layers of motion simultaneously. Earth's rotation carries you at roughly 1,674 kilometers per hour near the equator, about 1,040 miles per hour, which accumulates to approximately 40,000 kilometers of travel each day relative to Earth's axis. Earth's orbit carries you at approximately 107,280 kilometers per hour, about 66,661 miles per hour, which accumulates to roughly 2.5 million kilometers of travel each day relative to the Sun. The Sun's orbit around the Milky Way carries you at roughly 800,000 kilometers per hour, about 500,000 miles per hour, which accumulates to roughly 19 to 20 million kilometers of travel each day relative to the galactic center. Motion relative to the CMB carries you at roughly 1.3 million kilometers per hour, about 825,000 miles per hour, which accumulates to roughly 31.9 million kilometers of travel each day relative to the ancient background radiation. The 31.9 million kilometers per day relative to the CMB is about 83 times the Earth-Moon distance. In the time it takes the Moon to complete one orbit around Earth, roughly 27 days, you have traveled over 860 million kilometers relative to the CMB, a distance greater than the distance from Earth to Jupiter at their closest approach. All of this happens while you feel perfectly still. The stillness is real in your local reference frame, and the motion is real in other reference frames. Both are accurate descriptions of your state, appropriate to different contexts. Let me trace the historical arc once more, because seeing the development as a whole helps appreciate how far our understanding has come. In 1632, Galileo published his thought experiment about the ship's cabin, showing that uniform motion cannot be detected from within a closed system. This was a profound insight, but Galileo could not have known where it would lead. In 1687, Newton published his Principia, formalizing classical mechanics and introducing the law of universal gravitation. Newton's physics was spectacularly successful, but it left open questions about the nature of space and motion. Was there an absolute space in which all motion could be measured? Newton introduced the concept but acknowledged its difficulties. In 1887, Michelson and Morley performed their famous experiment, searching for Earth's motion through the ether. The null result was puzzling and prompted various attempts at explanation. In 1905, Einstein published Special Relativity, building on Galileo's principle and the constancy of light speed to derive time dilation, length contraction, and relativity of simultaneity. Space and time became unified into space-time, and the concept of absolute rest was definitively abandoned. In 1915, Einstein published General Relativity, extending his theory to include gravity and acceleration. Gravity became geometry, free fall became inertial motion, and space-time became a dynamic entity curved by mass and twisted by rotation. In 1918, Lense and Thirring worked out the frame dragging prediction, showing that rotating masses should drag space-time around with them. This was a theoretical prediction waiting for technology to catch up. Throughout the 20th century, increasingly precise experiments confirmed relativistic predictions. Atomic clocks measured time dilation. Particle accelerators observed length contraction. Solar eclipses and radio telescopes measured gravitational light bending. In 2004, satellite laser ranging measurements confirmed frame dragging around Earth at the 10% level. In 2011, Gravity Probe B confirmed it with orbiting gyroscopes. Each step built on what came before. Galileo's insight about uniform motion became Einstein's first postulate of special relativity. Newton's gravitational theory became Einstein's geometric theory of curved space-time. Lense and Thirring's prediction became Gravity Probe B's measurement. The arc from Galileo to Gravity Probe B spans nearly 4 centuries, a remarkable example of how scientific understanding develops over generations, with each advance opening new questions and possibilities. What strikes me about this history is the persistence required. The frame dragging effect predicted in 1918 was not measured until 2004, nearly a century later. The technology simply did not exist to detect such a tiny effect. Physicists had to wait for satellites, lasers, cryogenic gyroscopes, and precision gravitational modeling before the prediction could be tested. This patience is characteristic of fundamental physics. Some predictions wait decades or centuries for confirmation. Others may never be testable with available technology. The commitment to testing theoretical predictions, even when the tests require extraordinary effort, is what makes physics a rigorous science, rather than mere speculation. The frame-dragging measurements are not just confirmations of general relativity. They are explorations of the actual structure of space-time in our neighborhood. They tell us something real about the geometry of the universe we inhabit. That we can know such things, that we can build instruments precise enough to detect a 2-meter orbital shift per year and interpret it as space-time being dragged by a rotating planet, is itself remarkable. Let me discuss the practical applications of relativistic physics, because theory and application are deeply connected. GPS is perhaps the most familiar example. The Global Positioning System uses satellites in orbit around Earth to provide position information to receivers on the ground. The system works by measuring how long signals take to travel from multiple satellites to the receiver, then triangulating the position. For this to work accurately, the timing must be extraordinarily precise. Light travels about 30 centimeters per nanosecond, so a timing error of just a few nanoseconds translates to a position error of meters. The satellite clocks experience both special relativistic and general relativistic effects. Their orbital speed causes time dilation, slowing their clocks by about 7 microseconds per day compared to ground clocks. Their higher altitude means weaker gravity, which causes their clocks to run faster by about 45 microseconds per day. The net effect is that GPS satellite clocks run faster than ground clocks by about 38 microseconds per day. If this were not corrected, GPS positions would drift by about 10 kilometers per day, making the system useless. The corrections are built into the system at multiple levels. The satellite clocks are deliberately set to run slightly slow before launch, so that once in orbit, with the relativistic effects included, they match ground clocks. Software corrections are also applied to fine-tune the timing. Every time you use GPS navigation, you are relying on relativistic physics. Einstein's theories are not just abstract concepts for theoretical physicists. They are operational principles built into everyday technology. Particle accelerators are another application. When particles are accelerated to speeds approaching the speed of light, relativistic effects become dominant. The particles gain mass energy, making them harder to accelerate further. Time dilation affects how long unstable particles survive before decaying. Physicists designing and operating particle accelerators must use relativistic calculations. Behavior of particles at high energies cannot be understood with pre-relativistic physics. Gravitational wave detection is a more recent application. When massive objects like black holes or neutron stars orbit each other and merge, they produce ripples in space-time itself, gravitational waves that travel outward at the speed of light. Detectors like LIGO measure these waves by detecting tiny changes in the distances between mirrors separated by kilometers. The waves stretch and squeeze space itself, causing the mirrors to move by amounts smaller than the width of a proton. The detection and analysis of gravitational waves requires general relativistic calculations. The waveforms that detectors observe must be matched to theoretical predictions from Einstein's equations. Without general relativity, we could not interpret the signals or extract information about the sources. Since the first detection in 2015, gravitational wave astronomy has opened a new window on the universe. We can now observe collisions between black holes, mergers of neutron stars, and other extreme events that produce no light but shake space-time itself. All of this rests on the foundation that Galileo laid in 1632, that Einstein transformed in 1905 and 1915, and that generations of physicists have tested and applied ever since. The theory that seemed abstract and disconnected from everyday experience turns out to be essential for technologies and observations that shape our modern world. Let me offer one final perspective on what it means that rest is relative. Every culture throughout history has had some concept of motion and stillness. We observe things moving and things staying put. We walk, run, ride animals, sail ships. Motion seems like a basic feature of the world, something obvious and unambiguous. Physics shows that this obviousness is misleading. What seems obvious depends on scale and perspective. At human scales, in everyday situations, motion and rest appear absolute. At cosmic scales, in relativistic situations, they reveal themselves as relationships. This is a pattern in physics. Time seems to flow uniformly for everyone until you examine it closely and find that it depends on motion and gravity. Space seems to be a fixed stage until you learn that it curves around masses and twists around rotating objects. Simultaneity seems like an obvious concept until you realize that different observers disagree about which events are simultaneous. Our intuitions are not wrong so much as limited. They are calibrated to the range of experiences that were important for our ancestors' survival. Walking across savannas, throwing rocks, tracking prey. Nothing in that experience prepared us for speeds approaching light or gravitational fields near black holes. Physics extends our understanding beyond the limits of intuition. Mathematical reasoning and experimental testing let us explore regimes where our everyday concepts break down. The reward is a deeper understanding of how the universe actually works, even when that understanding conflicts with common sense. The relativity of motion is one such understanding. It tells us that the universe is stranger than we imagined, more interconnected, more subtle. It tells us that questions we thought were simple, like, how fast am I moving, turn out to be surprisingly complex. It also tells us something about the nature of knowledge itself. Understanding the relativity of motion required centuries of effort by many people. Galileo thinking about his ship's cabin, Newton formalizing mechanics, Michelson and Morley searching for the ether, Einstein transforming our concepts of space and time, Lense-Thirring predicting frame dragging, engineers building satellites and gyroscopes to test these ideas. No single person could have done this alone. Scientific understanding is cumulative, each generation building on the work of those who came before, asking new questions, developing new tools, pushing into new territory. The result is knowledge that would have been unimaginable to our ancestors. We can measure our motion relative to the cosmic background radiation, the light left over from the earliest era of the observable universe. We can detect the twist of space-time caused by Earth's rotation, an effect of less than 2 meters per year. This knowledge does not change our daily lives in obvious ways. You will still feel at rest in your chair, still experience the world as if motion and rest were absolute. But knowing what physics has discovered adds a layer of appreciation, a sense of the hidden complexity beneath ordinary experience. The next time you sit quietly, feeling perfectly still, you might remember that you are hurtling through the cosmos at hundreds of kilometers per second, tracing a path through space-time that curves and twists with the geometry of the universe, carried by motions you cannot feel toward destinations you cannot perceive. Motion is real, rest is relative, and the universe is far more remarkable than our everyday intuitions suggest. Let me reflect on what makes this understanding valuable. Relativity is not just an abstract theory about high speeds and extreme conditions. It is the actual structure of the space-time we inhabit. The GPS satellites in orbit around Earth must account for relativistic effects, both special relativistic time dilation due to their orbital speed and general relativistic effects due to the weaker gravity at their altitude. Without these corrections, GPS would drift by kilometers per day. The fact that your phone can tell you where you are within meters depends on Einstein's theories being correct, and on engineers understanding how to apply them. Relativity is not just physics for particle accelerators and black holes. It is physics for navigation systems and satellite communications. Frame dragging, though tiny around Earth, becomes significant in more extreme environments. Around neutron stars, the effect is stronger. Around spinning black holes, it dominates, creating regions where space-time is dragged so violently that nothing can remain stationary relative to the distant stars. The precision tests of general relativity, including the frame-dragging measurements from LAGEOS and Gravity Probe B, are not just confirmations of a theory. They are explorations of the actual geometry of space-time around us, measurements of how our planet twists the fabric of the universe. What I find most striking about all of this is how much we have learned with instruments of human construction. The Michelson-Morley experiment in 1887 used mirrors and beams of light to search for motion through the ether. They found nothing, and that null result helped pave the way for Einstein. Gravity Probe B in 2004 used cryogenic gyroscopes so perfectly spherical that their surface variations were smaller than atoms suspended in magnetic fields cooled to near absolute zero and tracked by a telescope locked onto a distant star. They measured the twist of space-time around a rotating planet. Satellite laser ranging uses pulses of light bounced off mirrors thousands of kilometers above Earth, timed to nanosecond precision over years of observations, to detect orbital shifts of less than 2 meters per year. These are extraordinary achievements of human ingenuity, patience, and precision. They demonstrate that the strangest predictions of theoretical physics can be tested and confirmed with instruments we build and measurements we make. The universe is not obligated to be comprehensible to humans. Yet, we find ourselves able to understand it, to measure its properties, to confirm predictions made from pure reasoning about the nature of space and time. This is remarkable, and it is worth pausing to appreciate. When Galileo imagined his ship's cabin in 1632, he could not have known where his insight would lead. He could not have anticipated Einstein's spacetime, frame dragging, or satellites measuring milliarc-second precessions. He simply noticed that uniform motion is undetectable from within, and he followed that thought carefully. From that simple observation came one of the deepest insights in physics. Motion is relative. Rest is relative. And there is no absolute background against which our true state can be measured. Let me bring this exploration to a close by returning to where we started. You are sitting still right now, feeling no motion, sensing no speed, experiencing what seems like perfect rest. In your local reference frame, attached to your chair and your room and your building, you are at rest. This is true and correct. At the same time, you are moving through nested layers of motion that accumulate to extraordinary speeds. Rotation with Earth's surface, revolution around the Sun, orbit around the galactic center, drift relative to the cosmic background radiation. These are not contradictory statements. They are descriptions appropriate to different reference frames. The concept of absolute rest, a frame-independent fact about whether you are truly moving or truly still, does not exist in physics. What exists is relative motion, motion measured relative to something, always specified in context. Galileo glimpsed this in 1632 with his ship's cabin thought experiment. Einstein transformed it into one of the pillars of modern physics. General Relativity extended it to curved spacetime and showed that gravity is geometry, that free fall is inertial, and that massive rotating objects drag spacetime around with them. We have measured these effects. Time dilation has been confirmed with atomic clocks. Length contraction appears in particle physics experiments. Frame dragging has been detected with laser-tracked satellites and cryogenic gyroscopes. The physics is confirmed, precise, operational. GPS satellites use relativistic corrections. Particle accelerators apply Lorentz transformations. Gravitational wave detectors exploit the behavior of space-time. What we have learned is not that motion is unreal, but that motion is relational. You are moving relative to the CMB at 369 kilometers per second. You are at rest relative to your chair. Both statements are true because they describe different relationships. The question, how fast are you really moving, has no single answer because it presupposes something that does not exist, an absolute frame against which your true speed could be measured. Replace that question with, how fast are you moving relative to x, and clear answers emerge, different for different values of x, all equally valid. This is one of the deepest insights of modern physics, and it took humanity centuries to arrive at it. From Galileo's intuition, to Newton's mechanics, to the Michelson-Morley null result, to Einstein's revolution, to the precision tests of our own era. The next time you sit quietly, perhaps late at night, perhaps watching the stars through a window, consider the motion you cannot feel, the rotation carrying you eastward, the orbit carrying you around the Sun, the galactic journey carrying you through the Milky Way, the cosmic drift through the ancient radiation that fills all of space. You are moving through all of these simultaneously, stacking velocities that point in different directions, tracing a path through space-time that curves and twists with the geometry of the universe. You feel nothing, because you are moving with everything around you, because uniform motion is undetectable from within, because physics does not privilege any frame as the one that tells you the truth about your state. Motion is real. Rest is not absolute. Space and time are woven together into space-time, curved by mass and twisted by rotation. These are facts about the universe we inhabit, discovered by human curiosity and confirmed by human ingenuity. The ability to know them is itself remarkable. Thank you for joining me on this journey through relativity and motion, through Galileo's insight and Einstein's transformation, through satellite orbits and gyroscope precessions, through the nested frames of reference that describe our place in the cosmos. If you found this exploration valuable, consider subscribing to the channel. It helps these deep dives reach more curious minds. Sleep well tonight, and as you drift off, perhaps picture the motion you carry with you, the 369 kilometers per second through the ancient light, the millions of kilometers traversed while you rest. Motion that is real, even as your rest is equally real in its own frame. Good night.